guys, welcome to the first video for section 1.2, which is really just we're going to do about half of the content in this video. And what we're going to do is we're going to look at representing functions, and then more specifically things that you need to know with linear functions, parent functions, and then we're going to talk about piecewise functions in a little bit more detail than what we've done in the past. Again, most of this is a review. We're just kind of making sure we're on the same page here as we take a look at it. Now, prior to this class, you did look at a lot of different functions. You have algebraic functions, which are things like polynomials, which includes lines, quadratics, cubics, and so on. Then you have your rational functions, where you have a polynomial divided by a polynomial. And then the ones that we studied last year in more detail, exponents, logs, trig functions, and there are many more. The transcendental functions are just called transcendental functions because they basically transcend the algebra that you have. They have extra stuff. That's the way I like to look at it. It takes a little bit more to solve a trig equation because it's not algebraic and like solve for x, subtract things from one side to the other. It has a little bit of extra into it. They're like specially defined functions to help us in some things. Alright, one thing I will say that all calculus students, you need to know your parent graphs and the characteristics. So you've already done an activity in Desmos where you did a parent graph match, and then we gave you a handout with some common parent graphs that you need to know. So make sure that you know those and commit them to memory, and you can quickly sketch them. You know their characteristics, domain, range, where they increase, decrease, maxes, mins, concave up, concave down, all of that stuff. Now, linear functions, I am going to say that the biggest thing is that you need to make sure that you can write the equation of a line in point-slope form. This is the most important one that we're going to use in calculus. We pretty much kind of consider we'll say the y equals mx plus b, the slope-intercept form, the toddler version of the equation of a line. But for calculus, we are going to always use this point-slope. You have your equation of the line, all you need, and this is what most of the time you have in calculus, is any point on the line. So we have x1, y1, so here's your x1, here's your y1, and then your slope m right here. Those are the only things that you need in order to write the equation of a line. Okay? So if I want to write the equation of a line that goes to the points 2, -3, and has a slope of 4, then what you're going to do basically is just fill in the blank. Here's my x1 and my y1, and so I put in the 2, and then notice right here that I subtracted -3, and so that gave me a +3 in that location. And then I filled in the slope of 4 where the m was here and here. So very straightforward, and then we're done. You do not have to solve for y. You don't have to put it in y equals mx plus b form. That is the equation of a line. Just write it and walk away from it. So we're saving you some work as long as you have a point and a slope. Now, sometimes you don't have a point and a slope, so you have to do the work. But given any 2 points, you should know the slope formula. So take any 2 points, change in y over change in x. So the second y minus the first y, second x minus the first x, and then go ahead and calculate that out. Fairly straightforward. And then once I have the slope, it actually does not matter whether you use the first point or the second point. They are both acceptable answers, and we'll take both of them. You just choose which point you want to use. So the first point, we would have the 6 and the -4, and notice that it's -6 plus 4. And then, wait, hold on, I have to sneeze. All right, sorry, a little pause there for sneezing. Okay, and then the second point, so you could use the y -8 equals -3, x -2. Both are acceptable answers. We don't need to do anything else. We don't need to solve for y, convert the forms, or anything. We'll take those answers. Now, so far we've only discussed this point-slope form, but there are other forms. So depending on what they ask you, you should be able to recognize the other forms as well. I have mentioned a couple of different things as we go, but let's start with a horizontal line. A horizontal line going across is going to be always a y equals a constant. So very quickly you should be able to come up with the equation of a horizontal line. Now, there there's a vertical line, and that's where, you're going straight up and down, and that's going to be an x equals, but we'll comment on that one. That is not actually a function, a linear function. It's just a linear relation because it doesn't pass the vertical line test. Then we have our slope-intercept form, the one you're most familiar with. So you can just solve for y and get it into this form, and that would give you an equation of a line. And then the last form that we do use is what's called standard form. And really all it is that you have the x's and the y's on one side. You have a, b, and c have to be integers as you're looking at that. And to write the equations in the last two forms, depending on what you have, if you don't have the slope and the y-intercept, but you have a slope and a point, just write the equation in point-slope form and then just solve for y. Standard form, same thing. You can do point-slope form and then just rearrange as we go. Alright, so earlier example, we had the 6, -4 and the 2, 8. And so suppose I want that same example but written in a different form. So if I want to go to slope-intercept form, I'm going to solve for y and simplify the right side and distribute the slope and so on. I mean, it's just basic algebra. You guys have this. So I moved the 4 over from this side to that side. I distributed the 3 through. That got me to here, and I collected like terms. So that gets us into that form. Now notice, I did the same thing. Here was the other form of that line. If I add 8 to both sides, move that over, distribute the 3, we still end up with it. They're the same equation, they're just different forms. So it doesn't matter which one you start with. If you're going to write it in the standard form, then what you want to do is start either in point-slope or slope-intercept, it doesn't matter, and you just need to make sure you put all the variables on the left side and the constants on the right side and clear fractions when you have it. If they are not integers, if a, b, or c are not integers, eliminate the fraction or the decimals. And when it says appropriate factor, remember you multiply by the GCF. And the GCF is going to get rid of the fractions that are there. So write each of these in standard form. So very quickly on this, first thing that we might do is subtract the 2/3, move it over to that side. That's getting all the x's on the same side. Then there's a 3 in the denominator, so basically you're just going to multiply by 3, the GCF, and it will eliminate the terms. There's my standard form. Now obviously, it would also be correct to say positive 2x minus 3y equals 12. That would work too. It doesn't really matter, positive or negative. Some people just like to have a positive on the first term, but it doesn't really matter. And then same thing over here, distribute your 3/2. That got me to here. Then I subtract the 3/2 x, and I move the 6, add 6 over to that side. That got me to here. And then multiply by 2 to clear the fraction, and I end up with that standard form. Alright, now, one last thing when we talk about this. If they ask you to write the equation y as a function of x, that simply means that you have to solve for y. The 3 ones that we kind of talked about, the only one that's actually already written as a function is the slope-intercept form. So the other ones, like this one, it says solve for y. Notice I did not put it in slope-intercept form. Sorry. I didn't put it in slope-intercept form. I simply just moved the +3 over to that side by subtracting. That is y as a function of x, and that is all we need to do. And we would leave it in that form. So if you have to write your function as a function of x, then you just have to solve for y to put it in function form. Alright, let's talk about piecewise functions. So piecewise functions, basically it's a set that has different pieces you're combining together, so different rules. And those formulas are non-overlapping, and the reason why they're non-overlapping is it's a function, so you can't fail the vertical line test, and they give you subsets of its domain, so in other words, they tell you where you want each piece. And to evaluate each function at a particular input value, you have to figure out which rule applies. And once you know what rule applies, you just plug it into that one rule, because the function should only have one output. And if you're going to graph that function, you need to graph each of the pieces and only the piece that corresponds to their subdomain. The first piecewise function that you should definitely be familiar with is absolute value. And absolute value, here is the formula version of it, And then the piecewise, you are y equals x, only when x is greater than or equal to 0. Notice that's my subdomain right there. And then y equals negative x if x is less than 0. So we have two pieces. We have a positive slope line when x is positive, and we have a negative slope line when x is negative. And that's our piecewise definition. Notice that 0 is only included in one piece because it's a function. So it doesn't really matter which one, but the convention is to put it with the first one. And evaluating it, if I wanted to find f of 3, I plug 3, take the absolute value, I get 3. You're really just using the top rule, because the top rule says if you're already positive, then return the number. But if you are negative, return the opposite of the number. So if you are negative, your input is negative, it returns, the absolute value returns the opposite of the number, which gives me 3, which is also known as make it positive, but that's why it's a piecewise definition. Now, one warning that I will say here is piecewise functions, most of them are discontinuous. Now, absolute value is continuous. It was connected and there's no holes or gaps or missing values or anything like that. But a lot of piecewise functions are going to be discontinuous, where you switch from one rule to another. And so that's something to pay attention to. Let's look at another example. So now we have a piecewise function, and that piecewise function, we have a parabola and we have a line. The parabola is only graphed on the section -2 to 1, and the line is only graphed from 1 to 2. So when I am evaluating it, if I do f of -1, that -1 falls in this first interval right here, so that means I only need to use the x squared rule to evaluate it, so f of -1 is 1. If I'm looking at the bottom rule and I want to calculate f of 1, 1 falls in the subdomain from 1 to 2 because of the equals, and then, so I use the bottom rule. So f of 1 would be 1 plus 1, x plus 1, and then I get 2. So you evaluate using whichever rule corresponds, the input is in the subdomain, so you check that out. Now f of 10, for example, is going to be undefined because there's no rule for x equal to 10. In other words, plugging 10 in is not allowed because the function does not have an output for 10. So we would say that f of 10 is undefined. You may also say f of 10 is D&E, does not exist, and that would be appropriate as well. What you can't say is null set. That is not appropriate for this. You're not finding a set or an empty set when you are evaluating a function. Either the function evaluates to a real number, or the function does not evaluate to a real number, which would make it undefined over the reals. That's kind of what we mean by that. Now, how do the pieces connect? The pieces could connect so that you are continuous. So here's an example where you have a line, a parabola, and a line, and they connect at a closed circle. So it's a continuous function. So you have different pieces, but the pieces nicely connect together. You could have the pieces connect, but instead of having a closed circle, they have an open circle. And so it would be, one of these things where it's discontinuous, but it still connects. It's just missing a single value. F of -2 for this example would be undefined. Over here, you can get where the pieces don't connect at all at x equal to a. And there's different things that could happen here. I put 2 of them in here. This is an example where at x equal to -3, that actually has an asymptote. So the 2 pieces, this piece and that piece, don't connect because they have an infinite discontinuity. One goes up, one goes down. They don't connect to each other. You could have a discontinuity like this one where they don't connect because there's a jump between the y values. This piece's y value is down here at 1, and then it jumps up to a y value up here at 6, and then the function continues on. Now, when you're looking at these, notice that you can't have a solid circle here and here. It can only be in one place. So you can either have both open or one closed, one open, but you can't have both closed because that would not be a function. When you're graphing, clearly indicate your endpoints and whether they're included or not included from the graph. Included is solid dot, not included is open dot. Alright, so when we're graphing, this one that we had earlier, we have a parabola and we have a line. So basically what I do is I'm going to graph y equals x squared, but I'm not going to graph the whole thing. I'm only going to graph on the subdomain from -2 to 1. Now the most important thing is really just to figure out your endpoints first, and then figure out the rest of the middle section that you're going to keep. So I first take the -2 and I plug that in and I get 4. So the left endpoint is at -2, 4. That's included in the subdomain because of the bracket, and so I'm going to make that a filled in circle when we do it. Now the second endpoint over here at 1, if I plug 1 into the parabola, the right endpoint is at 1, 1. Now don't get confused. When I am doing this graphing, I'm not finding a function value. I'm trying to figure out where the parabola piece stops. So why do I use the top rule instead of the bottom rule? Because I'm not finding a function value. I'm trying to figure out the end of the piece of the parabola at 1. So I'm plugging it into the parabola to find the end. But then I exclude it because of the parentheses, and so I put a hollow circle there. Now the bottom rule, same thing. This one is bracket on both. So it's a line segment. I get the left endpoint, I get the right endpoint, and because it's a line, you can just connect the two together. So we put our two endpoints on, and then we plot them as filled in circles, and this would be an example of what it looks like. So basic graphing with piecewise functions, you just need to graph each piece, make sure you get your endpoints, and then you can decide how they connect. And notice that in this one, this has two pieces that you went from a y value of 1 with an open circle, jumps up to a y value of 2, and then continues on, so they don't meet, and this is called a jump discontinuity. All right, another example, here's a piecewise function with a removable discontinuity. And you'll remember from last year, removable simply means that there is usually a hole in the location of where they're going to meet. So I have a line and then basically a single point. When I have x equals 3 and 7, that is really just giving you a point to plot. So we're going to first graph the line x plus 3, but we're going to leave a hole at 3, 6 because 3 is not included. We deleted 3 from the domain. When this is your subdomain, it means graph the line for everything but 3. And so that's why I'm going to put a hole at the point 3, 6. And then the bottom rule tells me where the point actually is for that. And we end up with this picture. And so this is what's called a removable discontinuity. And more specifically, it's called a removable point discontinuity. And the definition, if I say what's f of 3 is not going to be 6, it's going to be 7. F of 3 is 7 because that's where the closed circle is. Okay? If I wanted it to not be discontinuous, then f of 3 would have to be, of course, 6, which is not true in this one. It would be a different function. Now, there are two special functions that we're going to talk about in this section. And once we started talking about what calculus is, we've talked about the fact that the derivative is the slope at a certain value. So there's this idea that we could have what's called a slope function. So a little bit later on, that slope function is what we're going to start calling the derivative function. And that slope function is a graph of where you're just giving the slopes that you would have. Now, for a linear piecewise like this, linear functions all have the same slope. So the slope for the first piece, the line y equals 2x, is going to be 2 everywhere. The slope for the second line, y equals 2, is a horizontal line, so it would have a slope of 0. And the slope for the rest of this one goes down 1 and over 1. So the slope would be negative x, and so that's going down. So my slope function, notice what I've graphed is a new piecewise function, g of x, has a slope of 2 for the first piece, a slope of 0, and a slope of negative 1. and we have graphed each of these along. Now, I will tell you, just as kind of like a little coming attractions things, notice that I have open circles on where the two pieces met. And the reason that I have that is because at this point, it can't both have a slope of 2 and a slope of 0, depending on which piece you're including it on. So this is what's called a cusp. And when we do a cusp, because it's kind of like a teeter-totter when you're looking at it, it doesn't have a consistent slope, so it can't be part of the function, the slope function, because of the fact that there's two possible answers. So we're going to exclude that from the derivative or the slope function. And that's why both of these are all kind of taken out. We're going to talk a lot more about that in a later chapter. Now, not only can we talk about this derivative function, we are also going to talk about this area function. And so the second part of calculus, which was the integration, where you're working backwards from a derivative function back to the original function, this actually is something that's directly related to area. And that's kind of the preview that we had in the video that we watched. Now, this area function, okay, again, starting with something really simple, a nice little piecewise linear function, which has geometric shapes underneath of it. So if I want to find the area from t equals 0 to t equals x, it really turns into a geometry problem. So what the first thing is, as an example, I would like to find the area from 0 to 2, and that's what this a of 2 is down here. And then I also want to find the area from 0 to 5, and that's what this one is down here. So let's take a look at those. So this first one, so I just basically from 0 to 2, so from here to here, I drew the line, kind of connected it up to the curve, and I shaded it in. So I'm looking for the area of the region bounded by the graph, the x-axis, and the x equal to 2 line. And it's just a triangle. And we all know that the area of a triangle is 1/2 base times height, and so I just plug in, my base is 2, my height is 4, notice that's f of 2, and then I calculate out, and that's my area. All right, let's look at a of 5. So now this one, I want the area from 0 to 5, and so I've drawn the line at x equal to 5 up to the curve. Here's the curve and then the x-axis. So I shaded in that region. And so this region, if you look at it, is the area of the triangle plus the area of a rectangle. So area of the triangle is constant because it's the same. And then the area of the rectangle is 2 by 6. And again, notice that I'm using the function height, f of 6, or f of 5, I'm sorry, is how I'm getting 6 over here to get the height. So now, let's actually find a piecewise formula for this area function. So when I'm finding this area function, then you see that there's two cases. As long as x is in between 0 and 3, then the area is just going to be the area of a triangle. But if my x is somewhere between 3 and then beyond 3 up to 8, then it's going to be the area of a triangle plus the area of the rectangle. So see how there's two cases going on. So I'm going to set this up as a piecewise function. So the area for the first piece, anything where x is between 0 and 3, the area is the area of a triangle where the base is going to be x, that's this part right here, and the height is going to be found by the y value of f of x. And so that's why I have x as the base down here, sorry, the little slideshow thing down there, and then f of x is simply the height, so it's 1/2 base times height. The function itself for this piece, remember, was y equals 2x. And that's why I substituted in 2x right there, and then I just simplified and it ended up being x squared. Now, if I'm over here on this side, notice that it's the area of the triangle. Sorry. So can you guys just look down there? It's the area of a triangle, and notice that's a constant. It's a base of 3, it's a height of 6, so it has a consistent area of 3 times 3, 9 on that. So you'll always do 9 plus the area of the rectangle that's here. And the area of the rectangle, because we're not picking x, would have a distance from 3 to x. And remember, distance between numbers would be second one minus the first one. So that's where the x minus 3 comes in. And then the height would again be the y value of the function evaluated at x, or f of x. And remember that f of x, because that's a constant function, is 6. And that's where that 6 comes from. And then we just simplified it all down and got the 6x minus 9. So now my area function, as a piecewise function, would be x squared, as long as you're just doing the triangle area. And then 6x minus 9 if you have the triangle area plus the rectangle area. And we end up with a piecewise definition. So both of these are going to be important for calculus. That the whole idea that there's two sides of calculus. There's the derivative function, which is looking at the slope at any x value. And that derivative function, so the slope function, is something we're going to spend half of the year on. And then the second half of the year, we're going to be working with integration. And integration is looking at working backwards from the slope function to the original function. And that working backwards has to do with the area under the curve. So we create this area function that's going to allow us to work backwards and get a function back from knowing the slopes. And so that's kind of the two parts of calculus. And like I said, this is just an introduction. We're going to be doing, like I said, half of the year on the slope function and the other half of the year on this area function. Derivatives and integration, the two halves of calculus. And remember that they are directly related to each other through the fundamental theorem of calculus, which simply says that the derivative will give you a function, the slope function, and if I want to work backwards, I use this integration to work backwards, and so the two processes are basically inverses of each other. They undo each other as they work back and forth, and that's what we're going to look at for most of this year. Alright, so that's going to end up this video. We will have one more video on section 1.2 coming up later in the week, but this will end up our linear functions, everything you need to know about linear functions, parent graphs, know your parent graphs, and then these special slope and area functions that we're going to be looking at continually throughout this year.